Here's an exponential decay problem. Amelia dirties 11 diapers a day right after she's born. At 6 weeks, she only dirties 7 per day. Assuming this rate of decay continues, how many will she dirty at 12 weeks? And when does the model predict she'll only dirty 2 diapers a day? So, this is not theoretical mathematics. As you may have guessed, Amelia is real. She's my daughter. That's my lovely wife, Meredith, by the way. And when she was born, she dirtied 11 diapers a day. She's 6 weeks in a day right now, and right about 7. So this is rather important. You're helping out my parenting skills as you do this problem. Okay, so what do we have? Well, exponential decay and exponential growth deals with a formula that looks like this. The amount equals the initial amount, or the principal, times e to the RT. Okay? Now, some people use this as the interest rate. There's another version of this that looks like P equals P naught e to the KT. Different variables, same concept. I'm going to use this version, and we're going to plug in the key parts and figure out how many diapers she's up to. Okay, so P here is the initial number of diapers. At birth, that's times 0. So what we're doing is we're putting in 11 to start with. Now, this is a related set of information. When T is 6, A is 7. I'd like to know what rate that predicts. Now, this says that the rate, exponential decay, says that over time the number of diapers goes down, but it doesn't go straight down, it sort of decreases. That might be natural, okay? So as opposed to, let's imagine you had a straight line prediction. At time 0, if you had 11 diapers, at time 6, you had 7 diapers. If you were trying to predict this with a straight line, you'd say, well, at 12 you went down 5, go down another 5, and it's 2. And at 18 weeks, maybe you're at -3 diapers. Not quite as good as this exponential decay model. So how do we solve this? Well, I need to solve for a variable in the exponent. So first, I'm going to get this in the form of a basic exponential equation by dividing by 11. Now, to pull that out of the exponent, I'll take the natural log of both sides. The natural log of e cancels, so I just get r times 6. Getting r by itself, I get r equals natural log of 7 over 11 divided by 6. If you were going to approximate that, I did it beforehand, I'm going to keep 4 significant digits. It's -0.07533. You can see I've got those digits. So what I've done here is what I call build a model. Okay? So I've built a model. My model now is A equals 11 e to the -0.0. That's supposed to be a 7. 0.07533 t. Now I can use this model. I can use it to solve a problem like A, okay? This is the using part. I take this model, how do I predict what will happen at 12 weeks? I'm going to put in 12 for t. So A equals 11 e to the -0.07533 times 12. You can punch that into your calculator. It comes out to 4.45. or about 4.5. This model predicts maybe about 4.5 diapers a day at 12 weeks. Well, this is a little more subtle. How about B? How do we use a model for B? Well, I want to know when, in other words, I'm going to be solving for the t, is A 2. So I'm going to plug in a 2 for A. And I'm going to solve for t. And Amelia will be overjoyed that we'll know how many weeks until she's down to 2 diapers a day. So Now I need to get this to a basic exponential equation. So I'm going to divide by 11. Since the variable's in the exponent, I'll take the natural log of both sides. I'm trying to isolate t, so I'll divide by this term here. Oops, and I forgot my negative. And my 5. Where did the 5 go to? There we go. Negative 0.07533. That's the t value I'm looking for. I approximated it before I started filming, and that comes out to approximately 22.6 weeks. So with this model, she'll be down to only 2 diapers in 22.6 weeks.